Earlier in the year, we studied a very special type of growth that could occur for populations or in different situations. Most noticeably or traditionally, we talk about population growth even for people or for animals. And earlier, even in calculus, we began to talk about something called exponential growth. And exponential growth curve would look something like this. It usually had the very famous formula P equals P naught e to the kt. And of course, with e to some power, as you can see, we would expect our population to continue to grow larger and larger and larger. And according to this equation, we would actually expect the population to go up towards infinity eventually. Now, of course, in the real world, we'd sit there and say, now, wait a minute. If there was a population of animals, let's say it was rabbits or whatever type of animal you'd like to think of, in a certain area, you wouldn't expect that as time would go on that number would actually continually ever increase and go off to infinity. No, we see things level off. And what we're studying today, the logistics growth curve, is a much better descriptor of what type of population growth can occur. We can very well expect to see some leveling off. And as you look here, there is in fact going to be a horizontal asymptote. Now, the logistic differential equation that we have is highlighted here, dp dt. We're comparing the growth of population per time is equal to some constant times the population at a given time times m minus p. P is the population, t is the time, k and m are constants, but m is the maximum carrying capacity. M is going to be the value of y in this horizontal asymptote. And let's see why. As m is called, why is m called the maximum carrying capacity? We'll go back to this differential equation. As p gets closer and closer to m, as p would get closer to that maximum carrying capacity, this differential equation is going to be very interesting. Imagine that p approached m. M minus m would go to 0, would approach 0. So this right side of the differential equation would approach 0. And that's where we would expect not to see a change in the population with respect to time. We'd expect to see a leveling off, and that's corresponding to the graph there. So very quickly, let's take a look at example 1. And this is dealing with a logistic differential equation for bears. The growth rate of a population of bears in a newly established wildlife preserve is modeled by the equation written here. What is the carrying capacity for the bears? Well, I hope we can see that here. The 0.008 would be our K. Clearly 100 would be our M. M in this regard would be 100. We would expect that due to food restrictions, land restrictions, the bears won't be able to continue to grow in their population larger and larger and larger. There probably is going to be some leveling off. According to this differential equation, the population will level off at 100. Okay, for part B, what is the bear population when the population is growing the fastest? Now, to help us out here for B, if we look very closely at this differential equation, this dp dt is written in terms of P, and if we're looking very closely, we'll notice that this right-hand side is a quadratic. dp dt is equal to our 0.008p, 100 minus p. we could eventually get to a graph, and we will, but if we were to look at dp dt now on our y-axis, this would be the rate of growth with respect to time. P is going to be on our x-axis. So let's see. A lot of times when we look at parabolas in the past, and in Algebra 2 even, we'd be interested in finding the x-intercepts. We'd let y equal 0. And of course, very, very quickly, I hope you can see we could use the zero product property. We could see that p could equal 0, and 100 minus p could equal 0, meaning that p could equal 100. Also, if we were to distribute this 0.008p across, you would get actually a 0.8p minus 0.008p squared. This parabola clearly is going to be opening down. And so what we're seeing is we would expect to see x-intercepts at 0 and also at 100. We know that our parabola is opening down, and even without having to resort to calculus, we can know that by the symmetry of a parabola, that the vertex, which happens to correspond in this case to the highest point on the curve, must occur symmetrically between the x-intercepts. So if I were to average 0 and 100, go to that value right in between, we'd be at 50. So what is the bear population when the population is growing the fastest? 50. And please hear this, this is super important. This is going to be true really for any logistic differential equation, that the greatest rate of population growth, the population is growing the fastest whenever the population is exactly half of the carrying capacity. And you can do a quick summary of what we've talked about on the parabolas. You can see the logistic differential equation curve is always a parabola. And you can see that you're always going to have an x-intercept of 0 and an x-intercept of m. And that means that our vertex will occur at 1/2 of m. Remember that. It can save you a lot of time. And we can use that actually as a fact from now on. Okay, well, in any event, for C, what is the rate of change of the population when it is growing the fastest? So it grows fastest at p equals 50. So plug that in. Definitely go ahead and plug that in, and we'll see right here, if we were to just work that out, dp dt would equal 0.008 times 50, and here is 100 minus 50. And of course, we could work this out via calculator. We could even do this by hand. Again, we have limited time here for this video. So for right now, I'm just going to quickly type this in and get 20. Pay attention to units, though. Units are incredibly important. You can say, well, the rate of change is 20. Well, 20 what? Your population, your y variable in this regard, or what's acting as the y variable, would be bears. And t, of course, is going to be measured in years as we read up ahead. So when the population is 50 bears, the rate of change at that moment would be 20 bears per year. I should just say year here. All right, well, very quickly, let's go to the back. We're not going to have enough time to complete all of this just now, but we can at least get started. For example 2, A moose population has a growth rate of dp/dt equals 0.0003 p 1000 minus p. Well, of course, we know this is our K. We know this is our M. So what's the carrying capacity? Plain and simply, like a gift, we get 1,000. And by the way, if I were to ask the question, it's not written down here, but if I were to ask, what is the moose population when the rate of change for the population with respect to time is greatest, it would be, of course, at half of this carrying capacity value, like we were just saying, at 500. Well, let's just begin to look at B. We're going to have a part 2 of this video to finish it up. But it says solve the differential equation with the initial condition that P of 0 equals 61, and then investigate your solution relative to a slope field. And of course, that really just means type it in using your slope field program on your calculator, and very nicely you could get a graphical verification of what you're seeing on the calculator. Well, real quick, let's just get started. Whenever you're asked to solve a differential equation of this type, we're going to have to separate variables. The separation of variables, very, very important that we remember that. So in other words, we have two variables in this problem. We have P, obviously, and also T. And tell you what, I'm going to do just a little bit of house cleaning over here. Multiply both sides by dt, and I'm going to leave the 0.0003 over here. However, on the left side, I'm going to divide. I need to bring my p's over. I'm going to have 1 over p times 1,000 minus p. So at this point, what we can do is we can actually integrate. Now, if we're on our toes, however, we're going to know that this left-hand side is actually going to need a partial fraction decomposition. And that's what we were doing for our last lesson. In fact, just honestly the other day. So what we'll do real quickly is say, well, here's 1 over p, here's 1,000 minus p. You might remember we had a over p plus b all over 1,000 minus p. Okay, so look at your individual factors. If it's not factored already, you need to factor it then. But here we are factored very nicely. We're going to multiply through by the least common denominator. And again, just as we've been doing, I hope this is now routine. We would get a times 1,000 minus p plus bp. And tell you what, let's let p equal 1,000, in which case we'd have the equation 1 equals, well, this would be p is 1,000, so we'd get 1,000b. So that means that b is equal to 1 over 1,000. We could also let p equal 0. And if p is equal to 0, well, here we get 1 is equal to 1,000a. And that's going to lead us to a is equal to 1 over 1,000. So really we're running out of time at this point, but if I may, I'm going to come back and just real quickly rewrite that left-hand side now as 1 over 1,000 times 1 over p. That's your a all over p plus, and then we'll say 1 over 1,000 times 1 over 1,000 minus p. So that's like your a over p and your b all over 1,000 minus p. And of course we have this as our dp. We have 0.0003 dt.